Hello everyone, welcome to my fourth video lecture. Today we shall discuss about two-phase region. So here we can see one binary diagram which is consist of two components. One is copper, another is nickel. This binary diagram is also simplest one. That's why it's also called isomorphous system. So this copper nickel diagram, now it will be used for giving you a knowledge about two-phase region. So in my last lecture, I have told you regarding that one-phase region. Right now, I will tell about this two-phase region. So in this regard, I want to remind you that this copper nickel phase diagram is also known as isomorphous system, as this binary diagram is one of the simplest binary phase diagrams, and also these copper and nickel are showing complete solubility in both liquid and solid state. That's why this copper nickel phase diagram is also known as isomorphous system. So now come to the today's topic, which is a two-phase region. So here we have composition axis, and in this side we have temperature axis. This line is solidus line, and this line is liquidus line. Here we have liquid phase. In this side we have alpha phase, and in between this liquidus and solidus line we have alpha plus liquid phase, or liquid plus alpha phase. So this is the two-phase region. To know about this two-phase region, we will draw a tie line. So this is one constant temperature line which is known as tie line. Tie line. So the equilibrium will be seen in this tie line. So with this help of with the help of this tie line, we will discuss the equilibrium of copper nickel diagram. So this temperature, constant temperature, let us say this is T star. This constant temperature is T star, and here the composition is Cl, and where the tie line is cutting the solidus line, here it is C alpha or CS. CS, Cl and CS. So this is from the liquidus line. This is from the liquidus line. So this Cl will tell us about the composition of this liquid phase, and this is from the solid line. That's why we can know about the composition of solid phase at this point. Now, how much variable do we have? We know the formula of a variable, which is V is equal to P into C minus 1 plus 1. Plus 1 is for the thermodynamic variable, which is temperature. In this case, pressure is constant. I have told you from my last 3 lecture. So here we have two phases. So P is equal to 1, and we have two components, copper and nickel. So C will be 2, sorry, phase will be 2 and component also will be 2. So if we put the value of P and C in this formula, we will get V is equal to 3. So now for two phase region, we have 3 variables. So what are the 3 variables? One is Cl, this one. Another is Cs, this one. And the third one is this temperature variable, thermodynamic variable, which is temperature. So now we have 3 variables, 2 composition variable Cl and Cs, and 1 thermodynamic variable, which is temperature. So from that modified phase rule, which was F is equal to 3 minus P, we already have discussed about this formula. Here P is equal to 2, as we are talking about two phase region. So by putting the value of P, we will get degree of freedom is equal to 1. So for two phase region, variable is 3 and degree of freedom is 1. So from these 3 variables, Cl, Cs and temperature, we have to fix any one. So that's why we are fixing this temperature. Let us say this fixed temperature is right now T star. T star is the fixed temperature. This is constant. So now we have 2 variables, which are Cl and Cs. So for constant temperature, we have the tie line T star. So at this region, we have temperature is equal to T star. So from here, at constant temperature, which is T star, the line is tie line. One end of this tie line, which is cutting this liquidus line, this is giving us the composition of liquid state, and the another end of this tie line, which is cutting that solidus line, this is giving the composition of solid state. So by giving the temperature in this point, this Cl is constant. Let us say this is for copper, we have 70% of copper, and for nickel 30%, and in this case 10% of copper and 90% of nickel. So by fixing this temperature at this point, we have one constant composition for Cl. It is 70% of copper and 30% of nickel, and here also this Cs is constant, which is consist of 10% of copper and 90% of nickel. So by fixing this temperature, we can get the equilibrium state of this composition, also this composition, which are like this. Now we also can fix any of these two composition variables. Let us say we are fixing this Cs, composition of solid, and temperature is variable right now. So this line is parallel to the temperature axis, and from here to this position the temperature is increasing. So up to this point, this is all solid, and after this point we have only liquid phase. Between these 2 points we have liquid plus solid. So here, by adding or removing that latent heat, we are converting the state of the matter. If we add that heat, that solid will be converted into liquid state, and if we remove, then the component will be solidify. So by fixing this Cs, or we can say Cl also, we can vary the temperature. So like this we can find out the composition of Cl, the composition of Cs. Also we can find out the temperature. So this is our solidus line. So the composition is varying along with this solidus line from left side to right side. So let us say this temperature is 1200 degrees C, or this temperature is 1083 degrees C. This temperature is 83 degrees C, where we have only copper, 100% of copper. Now we are increasing the weight percentage of nickel. So here in this place, let us say this temperature is 1150 degrees C, and here the composition is 70% of copper and 30% of nickel. So for 100% of copper and 0% of nickel, the solidification temperature is 1083 degrees C, and if we change the composition, copper is 70% and nickel is 30%. Let us say the solidification temperature is 1115 degrees C, 1150 degrees C. Now let us take this composition, which is consist of 50% of copper and 50% of nickel. 50% of copper and 50% of nickel. Here also you can see that temperature is increasing. Let us say this temperature is 1250 degrees C. So this composition, This for this composition, the solidification temperature is 1250 degrees C. So below this temperature, the composition will be solidify, and at that temperature, the liquid phase will be starting. So above of this temperature, if we increase the temperature, that composition, the solid composition, is converting into liquid phase. So from here we can see, if we take this is as tie line, and temperature here, the temperature is 1400 degrees C. So the composition, again the composition will change. So let us say this composition is consists of 95% of nickel and 5% of copper. So again the temperature, solidification temperature has been changed, and now it is 1400 degrees C. So by varying the composition, we can change the solidification temperature of the component. Now I shall discuss about the questionnaires I got. In my previous lectures comment section, I have seen one of my students have shown his interest to know more about one phase region and isomorphous system. I am very glad to see that any kind of queries from my student side. You have some query, that means you are thinking deeply and listening my lectures with full concentration. So thank you for that. And the first question from your side was does isomorphous system show complete solubility of components in particular phase or not? So the answer is, I've already told you in my second video lecture that an isomorphous system is such kind of system which shows complete solubility in liquid and solid state. So yes, it shows complete solubility of the both components in each other in both liquid and solid state. If we consider a solid phase, in this case, the both components will be soluble in each other. And if we melt them at high temperature, means above of their melting point, and let them become liquid, then also we can see that they are showing only a single element or alloy. As in this case also, they are complete soluble in each other. And now the second question. So the second question is the concept of one phase region applicable for isomorphous system? So to know about the answer of this question, at first you have to know about the definition of phase, which I already discussed in my classes about that phase component and all, and I also have given some examples of to differentiate between composition, component, phase, state and all. Now one phase region means either liquid phase or solid phase. So any system can show one phase region. Not only isomorphous system, it may be any kind of system. So now the third question. So one of my student asked me to elaborate isomorphous system as simplest of binary diagram. So we have lots of binary systems like that aluminum copper system or aluminum copper phase diagram, which is a very complex diagram. Beside this, we have bismuth cadmium diagram also, which is a eutectic diagram consists of two components. Okay, so in bismuth cadmium diagram we have two components. One is bismuth and another is cadmium. So as we have two components, that means this is one binary system. But this diagram is not that much simple like the previous one which we have discussed in my last class and in this lecture also, which is copper nickel phase diagram. Even we have the tin lead phase diagram. This is also a binary system, but not simplest. We have iron carbon diagram, silver but platinum diagram. These are also binary diagram, as all these are consist of two components. But these are not simplest. These are very complex diagram. So only simplest and which are completely soluble in both states are called isomorphous system, like that copper nickel phase diagram. That's why this copper nickel phase diagram is known as isomorphous system, which is a simplest one from these binary phase diagrams. So if you have more questions or more queries, you can ask me in my comment section. So thank you for today.